section 4.5, we'll be discussing the extreme value theorem and the mean value theorem. Let's first discuss some definitions. So these are just like the technical mathematical definitions of absolute maximum and absolute minimum. So f of c is the absolute maximum value of f of x if and only if f of c is greater than or equal to f of x for all x in the domain of f of x. That just means this value is bigger than or equal to every other value in that domain. And same idea with absolute minimum, except it switches to f of c is less than or equal to f of x. So it's the smallest x in that domain. We could also restrict it to a specific interval, which is most of the cases that we'll be talking about today. So a function does not have to reach an absolute maximum or minimum on its domain or on an interval. Sometimes it won't reach it. In this figure, number 1, we have the function x squared plus 1. It has both a maximum and a minimum. So my minimum is here at x equals 0. My maximum is at x equals 2. However, if I change and don't have closed points there, if I make these open points at the end, I no longer have a maximum point. I won't actually reach that highest point. I do still have a minimum. Or if I take out a point in the middle, so in essence I'm making my graph not continuous in between those 2 points, then I may not have a minimum. I would have a maximum though. And so we want to figure out a way that we can tell when a function will have absolute extrema. In order to do that, we will use something called the extreme value theorem. So first of all, if a function is continuous, this is like one of the most important ideas in calculus. Our function is continuous. And the other thing is that we are on a closed interval from a to b, so I don't have open points like in figure 2. Then f has both an absolute maximum and an absolute minimum y value on the interval, and it will either be at a critical point or an endpoint. So if you notice up here in my first graph, my minimum was at 0, and I had a horizontal tangent there. That's a critical point. My maximum, though, was at this endpoint. So they will either occur at the endpoints or a critical point in between. Now, just because a graph is not continuous or it's not on a closed interval doesn't mean it does not have an absolute max or min. It just means it doesn't have to. So for example, here, in figure 2, I do have a minimum but not a maximum, and in 3 I have a maximum but not a minimum. And so I'm not guaranteed to have both of those, but I could possibly have them. In question 1, we're given a function f of x, which is x plus 4 over x minus 1 times x plus 3, and we're on this closed interval negative 5 to 5. On which of the following closed intervals is the function f guaranteed by the EVT? So I'm going to go ahead and highlight EVT. I know I'm going to use extreme value theorem to have an absolute maximum and an absolute minimum. And so it's giving me certain intervals here that I have to look at. They are all closed, so that's okay. Sorry, I don't know why we shot back up. They are closed. The other thing, though, the EVT said is that I had to check to see if it was continuous. And I'm not sure about that. We'll have to think about it. So let's think about this graph, x plus 4 over x minus 1 times x plus 3. Where is that not continuous? So if you think about the graphical features, think back to pre-calculus, there's a vertical asymptote at x equals 1 and x equals negative 3. So that means the graph is not continuous at those 2 x values. So when I'm choosing an interval here, I have to make sure my interval does not include 1 or negative 3. Those are the only 2 places where my graph is not continuous, so any other interval that doesn't contain those should be good. So negative 5 to 5, that does include both 1 and negative 3, so that can't be it. Don't be confused because that's the interval they gave us. We're trying to restrict it down to an interval where we know we'll have a max and a min. Negative 3 to 1, nope, that can't be it. We can't actually include those endpoints. If it were parentheses here instead of closed, then we could think that it's continuous there. But again, we can only use closed intervals for EVT. Negative 2 to 0, that doesn't include 1 or negative 3, so that's probably our answer. Let's go ahead and double check D though. From 0 to 5, that does include the x equals 1, so that will not be our answer. So here our answer is C, negative 2 to 0. Let's actually start thinking about how to find where the absolute extrema are. So in order to find the extrema of a continuous function on a closed interval, we said by EVT that those would occur at either a critical point or an endpoint. So we're given the endpoints. That's the A to B. So we need to find the critical points next. So we'll find our critical points. Then what we're going to do is evaluate F at your critical points and your endpoints. So essentially you're just plugging those X values back into F to figure out which one is the smallest, the absolute minimum, and the greatest, the absolute maximum. So this step is called the candidates test. Our candidates are the critical numbers and the endpoints, and we're testing them to see which is the biggest and the smallest. If it asks you for the actual maximum or minimum value, that's a Y value. If it asks you where it occurs, that's an X value. So pay attention to the verbiage that's being used in the question. In number 2, it asks us to find the absolute extrema. So when it says extrema, that means maxes and mins of f of x on this interval from -1 to 2. So first we have to check, is this continuous? F is continuous since it's a polynomial. Any polynomial is always continuous and differentiable. We are on this closed interval from -1 to 2, so now we can go forward and find our candidates. So we're going to find our critical points first. So f prime is equal to 12x cubed minus 12x squared. We'll need to see where that's equal to 0. We could think about where it's undefined, but we know it's differentiable everywhere. So we factor this out. We get 12x times x squared minus 1 equals 0. And so that gives us our zeros of 0, 1, and -1. For the candidates test part, we're going to make a table of values with x and f of x. So pay attention here that this is f, not f prime. The f prime helps us determine what x values to use, but I want you to pay attention, this is f of x that we're plugging it back into. We're plugging it back into the original equation. So we need to include our endpoints and these x values here. Those are our candidates. So I'm going to put them in numeric order. It doesn't actually matter if you do or not. -1, 0, 1, and 2. Those are just our possible places where our maxes occurs. In order to figure out what the max and min are, we'll have to plug them into, again, this original equation. So if I evaluate this at -1, 3 times -1 to the 4th is 3, minus 4 times -1 cubed, that would be plus 4, so this is 7. If I evaluate at 0, that's 0. Evaluate at 1, that'd be 3 minus 4, that's -1. And if I evaluate at 2, I would have 3 times 16, which is 48, minus 4 times 8, so 48 minus 32, that's 16. So now I still need to analyze this table. I'm looking for my maximum value and my minimum value. My maximum value is here, 216. I'm looking for the biggest y value, by the way. And my smallest y value is here at -1. Now pay attention to what the question is asking you for. This says find the absolute extrema. I feel like it's a little vague about whether it's asking the x value or the y value. So I could just say this is my min, this is my max, but we probably want to say a little bit more than that. So we'll say f has an absolute min of -1 at x equals 1 and an absolute max of 16 at x equals 2. You have to be careful here. You never want to write these as coordinates. So please do not write them like -1, 1. That would actually make you lose points here. As usually we're talking about the y values, and so if we write it this way, we can be clear about which part is the y value, which part is the x value. In number 3, we have g of x equals absolute value of x minus 3 times absolute value of x plus 1. It asks me for the absolute minimum value of g on -2, 2. So again, when it says value like that, that does mean y value. Okay, so This absolute value function looks a little challenging to deal with for derivatives. So maybe there's a different way to think about the critical points. So what we want to do is think about where g prime of x is undefined. Where is g, in other words, not differentiable? Those are going to be our critical points. And so when we think about absolute value functions, we know they look like a v. And to figure out where that corner is, we look at the vertices of your absolute value function. So we can look at these two separate functions. These are going to give me my critical points. So absolute value of x, that vertex is just at 0. I'm essentially just setting the inside part of the absolute value equal to 0. And then x plus 1 is equal to 0 at -1. So those are my critical points. I don't actually have to find the derivative in this case to do this. All right, so now I'm going to go ahead. I have my endpoints as well. And I will plug that into this absolute value equation, my g of x in this case. I'm going to evaluate at -2, at -1, 0, and 2. Once again, it's my critical points from here, my endpoints from here. If I evaluate at -2, I would have absolute value of -2, which is 2, minus 3 times -2, the absolute value of -2 plus 1, so that's just -3. That gives me -1. If I evaluate at -1, I would have 1 minus 0, which is 1. Evaluate at 0, I would get 0 minus 3, which is -3. And evaluate at 2, I'd have 2 minus 3 times 3, or 2 minus 9, which is -7. This asks me for the absolute minimum value, and so that is just -7. Okay, I don't want to include the x value here when it just asks me for that value. Now for those last two examples, you could have just graphed the equations and looked to see where the biggest value is or the smallest value is. And that's not really doing calculus. And so what you'll see sometimes is some problems will ask you about the derivatives instead, and then ask what kind of conclusions you can make about absolute maximum and minimum values. So this is a little trickier because we don't actually have the graph of our original functions. But let's look and see what we have here. So here we have f prime of x. And so we're starting here at -5, and we have this shape here. One thing I want you to notice is that f prime of x is greater than 0. It's always greater than 0 here. If I follow this graph, it's always positive. That means f is always increasing. So I don't really have to, I'm not going to actually sketch out this graph, but I start at some y value at -5. And then I'm always increasing. And then I end at 5. So this is my sketch of f of x. It doesn't actually look like that, but I know it's always increasing. So what I can tell is, since f prime of x is greater than 0, then f is always increasing. Just trying to write out a little justification here. And what that means is the point where I start at has to be my smallest, and the point that I end has to be my biggest. So think if I'm walking uphill and I'm always walking uphill, my lowest point would be where I started, my highest point would be where I would end. So what I can say is, therefore, f has an absolute min at x equals -5 and an absolute max at x equals 5. Now I cannot tell what those values are, I can only tell where they occur. If I had my original function, I could figure out what the value is. I just know that that's the smallest and that's the biggest. In part B though, you'll notice that we have a shift here. So I start out negative, and then it's positive. So what that means my graph is doing is I'm decreasing first. I have some point that I'm starting at. I decrease, and then I start increasing. Now, I don't know for sure if this point over here is smaller or larger than where I started. We'll be able to figure that out later in the year. But for right now, all I know is that I do have this relative minimum right here at 4. And what we know from our previous sections is that I have a relative minimum because G prime is changing from negative to positive. So when I only have one critical point here, that will either be an absolute max or an absolute min, and it will match up with whether or not it's a relative max or relative min. So what we can say is G has a relative min at x equals 4, since G prime changes from negative to positive. This is also an absolute min, since it is the only critical value. On this interval from 0 to 10. Now, we won't be able to tell about the absolute max, again, because we can't compare the endpoints, but I do know for sure that this point here at 4 is my absolute min.